In this section, we are going to talk about one of the most confusing term in the artificial intelligence, which is AI parameters. You have probably heard people say things like this model has 7 billion parameters or that model has 600 billion parameters. But what does that actually mean? Does having more parameters automatically makes an AI smarter? Why are AI companies racing to build model with a billion of parameters? And as a user, why should you even care? In this session, we will dismantle AI parameters, understand what they really are, how they help a model learn, and why they play such an important role in the modern AI. We will try to understand, help with this diagram, why is there a race for the more parameters. So now imagine you're building a library, and this is library A, somewhere around 10 shelves, and that holds around 1000 books. Now the library B 1000, and that can hold around 100,000 books. Which library can store more knowledge? If that's the question, the answer is very obvious, the library B, obviously. Parameters are very similar in nature. They are the kind of the storage capacity of the neural network. The more parameters you have, the more relationships the AI can learn. Now think about a model which is 100 billion parameters. Now it begins to learn grammar, programming, mathematics, biology, medicines, and there are many more. And the reason behind there is enough capacity. The key point is there is no known point where we can say now the model has learned everything. As models become more capable, they often acquire more new abilities. But that does not mean that there is no more abilities left to discover. Parameters represent a model's learning capacity, not its intelligence. As we increase the capacity and improve how models are trained, new capabilities may emerge. We don't yet know the ultimate limit of AI, which is why AI research continue to evolve. Today's race is not simply to build the larger models, but to discover better way for the models to learn and solve complex problems. Every AI company has its own secret recipe, just like the famous restaurants keep their special recipe secret. Some companies tells everyone how many parameters their model has, while others keep that information private because it's a part of the competitive advantage. Think of the parameter as a number of the pages in a student's notebook. A notebook with more pages has more space to write and remember things. Similarly, a model with more parameters has own capacity to learn and store knowledge. So if you see on the screen, some of the models, they're not disclosing how many parameters this model was trained on. However, there are models, they openly disclose those parameter capabilities. But having a bigger notebook does not automatically make someone smarter. That means if I train a model on 1 trillion parameter, is it going to outperform? Maybe, may not be. So think like if the notes are messy or incomplete, a smaller notebook with the well-organized notes can be much more useful. In the same way, AI models also depend on the quality of the training data, which is the most important thing. If your training data is wrong, your predictions are also going to be the wrong. Apart from the training data, their design and how they are trained, not just the number of the parameters. That's why some newer AI models with the fewer parameter can perform better than much larger, older models. With a very small number of the neurons and the layers, let's try to understand how these billion parameters are basically built or formed. In this example, we are talking about input layer, which has the 3 neurons. Then you have a hidden layer, which has the 4 neurons, and the output layer that has only 1 neuron. So parameters comes from the weights. Where the weight comes, this is the connection between the neurons, and every connection will have some weight. And then you have a bias. So here, let's try to calculate if this is the model, how many parameters in total it is going to have. On the input layer, how many weights we have? 3 neurons, connection to 4. They are going to form 12 connections. So you can think like this: 1, 2, 3, 4, 4 plus 4 plus 4. So total number of connections here are going to be 12. Then, based on the number of neurons in the hidden layer, those many are going to be the biases also. So here you see the 4. So I'm going to add 4 here as well. So 12 plus 4, that gives a value of 16. Then the hidden layer. What is happening on the hidden layer? Hidden layer is having 4 connection to the output layer. So 1, 2, 3, and 4. Plus 4. And then you will have one bias. The bias comes from the next layer. And here you have only one neuron, so plus 1. So 12 plus 4 plus 4 plus 1. And that value is going to be the 21. That is how you are going to calculate the total number of the parameters for a given model. Now, when we talk about the DNN, which is going to be the deep neural network, what basically we do there, we are going to add more and more hidden layers to solve the more complex problem. So I'm not going to talk about the DNA and how it works, but let's think about if we keep adding those layers, more neuron on every layer, then how these parameters will increase. So here you see 3 neurons on the input layer, 4 on the first hidden layer, another 4 on the second hidden layer, and this remains 1. So now what we are going to do, 3 neurons will form total 12 connections to 4 neurons. So 3 into 4 is equal to 12. Then you have bias for this layer, the layer 1. 4 neurons means 4 biases. Then comes to the next layer. You are forming 4 neuron to 4 neuron connection. Those are going to be 16. Then here you have 4. That number is here. On the hidden layer, 2. How many connections? 4, 1, 2, 3, and 4, plus 1 bias which comes from here. That is going to be 4 plus 1. If you add all these things, 16 plus 20 plus 5. So now the model becomes 41 parameter. This is how the model will look like if you say a model is trained for 1 billion parameter. So you'll have the input layer, and for example, there are 10,000 features. Then you have a first hidden layer, and let's assume 4096 neuron here. On the layer 2, again 4096, and then you have layer n, that is again 4096, and then the output layer, you have 10,000 neurons, and the total number of hidden layers is here. The n is equal to 80. If you calculate all the bias and the weight for each connection, then you are going to reach this value. This comes from the terminology when you train a model on a particular data set. So how do we train a model? Technically, you will train a model on the same dataset multiple times. And every cycle you can call it one epoch. For example, if your data sheet is having 1000 rows, so one epoch is equal to reading 1000 rows once. 10 epoch means reading all 1000 rows 10 times. So what it mean to us? So we'll continue to train the model until we get the right predictions. So is there any going to be the number, fixed number, how many epoch basically we need to train a model? Technically, there is no fixed number. It depends on that data set and the problem you are trying to solve. The another terminology which you're going to see is going to be the learning rate, and let's try to understand with this diagram what it means by the learning rate and why it is very important. So the goal of training is to find the parameter that can produce the lowest possible loss, and the lowest possible loss means higher the accuracy of the prediction. So early in the training, the model's weight are still far away from the good value. So you can afford to take the bigger, more aggressive steps to make fast progress. Later in the training, when the model is getting closer to the good solution, you want to take the smaller steps, more careful steps to fine tune without overshooting or bouncing around the optimal point. So let's imagine this is where I want to reach, and I'm here on the top. So initially I can take the bigger steps, and then when I come closer, I need to take smaller steps to reach the point. Don't pay too much attention on the formula and the graphs here. Let's try to understand, because this is also one of the terminology which we are going to see in the demo. So the common activation functions, these are going to be the linear, ReLU, Sigmoid, and Tanh. These are not the only one, there are more, but let's try to understand what exactly they do. So these activation functions are the decision makers inside a neural network. They decide what information should move forward, helping the AI learn useful pattern and ignore less useful information. This is the playground from the TensorFlow, and whatever the terminology and the techniques we already talked about, you can play with that. So here you see you have option to adjust how many neurons you want for that particular layer. You can add it, you can delete it as well. How many layers you want. So let's start from one, and you can keep adding more and more. So this adjustment you can do here. Then you have epoch option. It will tell how many epochs you need for a given data sheet. Then you have a learning rate. A learning rate is basically initially when you want to reach to the accuracy, you are going to take the bigger steps, and then when you're close to the goal, your steps should be, or maybe your learning rate goes down. So we'll choose 0.03, which is good enough. Then you have an activation layer. These fours, we already talked about it. Then the problem which you're going to solve, your problem can be classification, it can be regression. So with this, let's add one more hidden layer, and you see the test loss is around 0.132. This is your training loss, and let's start it. Now you can see within just 100 epoch, your test loss and the training loss goes to 0.000. So you can also try from your browser and see how these neural networks going to work in reality. This is just a simulation. Thank you for watching, and I will see you in the next episode.